Okay. Where did we leave off last time? Inverse functions. Does anybody have any questions about inverse functions? Okay. And I believe I've assigned the homework for that section. Okay. So now it's time for 6.2 inverse trigonometric functions and their applications. Okay. So an inverse trigonometric function is like so. Let's say we want to plot sine, and you guys know how to do this now. I don't have to even say it. But sine goes like this. And you can discover this if you create an f of x table. It peaks at pi over 2 over here, and it becomes 1. It goes down here to -1. Well, it's 0 here at pi. And it goes down here to -1 at 3 pi over 2. And over here it's 0 again at 2 pi, and it just continues on. Notice that this is a bona fide function because what kind of test does it pass? What? Correct, Travis. It passes the vertical line test. But recall, with our inverse functions, remember when we had, let's say we had f of x is equal to x minus 2. When we wanted to find the inverse function to this, we first said, okay, let's set this equal to a y, and then flip for every x, put a y, and every y, put an x. Resolve for y, and you got your inverse function. Such that, you know, for instance, this right here is the inverse of our f of x, which is x minus 2. And that equals, I want to stick that into our f inverse, I put x minus 2 plus 2. The 2's cancel, so you just get x. And over here, f of f inverse of x, f inverse of x is this x plus 2. When you plug it into f, we get x plus 2 minus 2. So then this equals x. You guys remember that? So what's happening when you switch x and y? What was x before and what was y before? Notice your y is equal to an f of x. When we create f of x tables, what goes down in this column? All of the what? The inputs, right? What goes down in this column? All of the what? Outputs, right? What is the fancy math term for inputs that work? Yeah. And what is the fancy math term for outputs that work? Range. Yes. So notice that in our algorithm for computing an inverse function, that one of the main parts of that algorithm is switching x and y. What does that effectively do? It flips the domain and range. It makes the new range what the old domain was, and it makes the old domain what the range was. When you flip x and y, the domain comes over here and the range comes over here. So I'll show you visually right now that sine inverse is going to end up look like this. This is what our sine inverse will look like. And it's going to be a function. And I'll tell you why. We're going to arrive at this fact together. Okay? But what we aspire to do is find a function. And notice that once we get to this point, this is really chopping this function up from here to here and doing a rotation. Okay? You'll see what I mean here in a second. First, let's define what a trigonometric inverse function really means. What is the sine of, let's say, pi over 4? What does this equal? Yes, you're correct, Pam. What is square root of 2 over 2? What does it represent?
A leg and the hypotenuse of the triangle formed in the unit circle.
Yeah, it's one of the legs in a right triangle formed at the unit circle for the angle pi over 4. Right? It's a length. So sine or cosine, whenever we input an angle, it's going to output a length. So let's just write that in mathematical symbols. Sine of some theta is equal to a L, a length, right? So that's why we're going to evaluate sine inverse of lengths, and they're going to output angles. Let me show you how we get to this step. We say, oh, just like you said, if I had an f of x is equal to y, what happens when I take f inverse of x of both sides? Well, I get f inverse of f of x is equal to f inverse of y. But f inverse cancel out, so I just get x is equal to f inverse of y over here. Do we not? Similarly, so right here, if we were to take the sine inverse of both sides, then that would imply you would get the sine inverse of sine of theta, and that's equal to the sine inverse of your L. And that's what ends up equaling this. Because the sine inverse disintegrate, you just get your theta, and the sine inverse of L remains. Now, let's discuss what sine inverse of L is asking you. And the best way to do so is to create a table. Whoa. My erasers are jumpy today. Let's create a sine of L. A sine inverse of L table. Let's plug in various lengths and see what the sine inverse outputs. What does sine inverse output? It outputs an angle, does it not? So let's go back to that question. What is the sine of pi over 4? Pam answered that it's root 2 over 2. So what happens if I take the sine inverse of both these? If I take the sine inverse of both sides, it's not multiplying by a sine inverse, by the way, guys. It's taking the function composition of sine inverse of both sides.
Would it be sine inverse of square root of 2 over 2 equals pi over 4?
Yes. Yes. That's right. Yeah. So how about for one of our lengths here, let's say root 2 over 2, we have that this equals pi over 4. Similarly, we could have a 0 here, or wait, maybe I should put this right here. No, actually, that's fine. Yeah, actually, no. I'm just scooting it down. So now, instead of inputting an angle into sine and outputting a length, now we're inputting a length into sine inverse and outputting an angle. So what would be the sine inverse of 0? It's an angle. It's asking you a question. It's saying at what angle, or at what angles, plural, does sine evaluate to equal 0? What angle, if I feed sine, it spits out a 0? Or what angles, plural? Well, if the angle is 0, sine of 0 is 0, is it not? Furthermore, sine of 2 pi is 0, is it not? Oh, furthermore, sine of 4 pi would then be 0, would it not? Sine of 6 pi would be 0, would it not? So actually, sine inverse of 0 is equal to 2 n pi, where n is an integer. Positive or negative or 0 integer. Just an integer. When it's 0, when n equals 0, we restore this output. When n equals 1, we restore this. When n equals 2, we restore this. When n equals negative 1, we'll get another one that works. So, if we want to say, okay, restrict our inputs, restrict our outputs, let's restrict the range. Let's restrict the range and say, okay, let's let theta range only from 2 pi and 0. And let's not include 2 pi, because then we'll have 2 outputs, won't we? We just want one output for sine inverse. So when we restrict the range like so, then it's only one of them, it's 0. So this question got answered. At what angle does sine output a 0? And if you don't see that, all you got to do is start off with like this. What is the sine of 0? 0. Take the sine inverse of both sides. And then you get 0 is equal to sine inverse of 0. So you can play this game for any of them. So what's the sine of pi over 3?
1/3 of 3/2.
Yep. That means when you take the sine inverse of both sides, you get pi over 3 is equal to sine inverse of root 3 over 2. And hence we put this right here. Does that make sense? The sine inverse asks you a question, just like the sine asks you a question. Sine asks you this question. I am sine, you input an angle into me, and I will output a length. Sine inverse is different, it's the reverse, because the domain and the range flips. Sine inverse says, I am sine inverse, you input a length, and I will output an angle. Make sense? So what would be the sine inverse of pi over 2?
Can you even do that?
Yeah.
It would be.
So that's a question. It asks you at what is the, it asks you the question. Sine inverse asks you the question. At what length of output, at what angle is sine of pi over 2? At what length does it output? So sine of pi over 2 says at the angle pi over 2, what is the length? Sine inverse, oh, no wonder you're confused. Okay. All right, yeah, that's why you're confused. So now does this make sense? So then you're inputting a length, it's outputting an angle. It's saying at what angle is the length of sine equal to 1? So I had just written the answer in those parentheses. I had a slip up. Does that make sense?
So with the sine inverse, can you input the angle in there?
No,
Okay, that's what.
that's not what it eats.
Okay.
Sine inverse eats lengths and spits out angles. But sine eats angles and spits out lengths. They just reverse each other. So why don't we plot this? Oh, and by the way, this is a necessary component for keeping it a function, and you'll see why. The restriction of the domain. Without that restriction, it will not be a function anymore. It will fail the vertical line test. So we created a L theta table, right? Here's L, here's theta. Let's plug in our various L's. 1/2 root 2 over 2, 3 over 2, 1. Let's say we have that. So then let's pick our angles. 5 over 6, 5 over 4, 5 over 3, 5 over 2. So we go to 0, the length 0, the angle output is 0, and we put a dot. Then we go to 1/2. What is the angle output? Say what? Yeah, sine inverse of 1/2 is pi over 6. So at 1/2 is outputting a pi over 6. At root 2 over 2, what is it outputting? And at root 3 over 2, what is it outputting? And at pi over 2, what is it outputting? Let's continue the table. Okay. Let's continue the table. And another thing we could have done was input negative values. Now that we know these, why don't we input the negatives and plot them? We had 0, that's 0. Actually, let's start out with the farthermost negative. Negative 1, negative root 3 over 2, negative root 2 over 2, negative 1/2, put 0 here. So what would the sine inverse of negative 1 be?
Negative pi over 2.
Negative pi over 2. Let's see. What is the sine inverse of negative 1 equal to? Well, it equals a theta, doesn't it? It equals some angle. Then what you can do to undo the sine inverse is take the sine of both sides. So you get negative 1 is equal to the sine of theta.
So it's just negative 1.
No, we're looking for what is theta.
Oh, yeah. No.
So sine inverse of negative 1 equals theta asks you, at what angle does the length of the sine function output a negative 1? What angle is that?
Negative pi over 2.
Negative pi over 2, yeah. Yeah, because that's the same thing as 3 pi over 2. It's in the same spot. But we notice that sine of negative pi over 2, here's your check. Let's check, what does this equal? Sine is an odd function. So we put the negative out there, so this becomes a negative 1. So that's correct. It is negative pi over 2. Does that make sense? So what is the sine inverse of negative root 3 over 2?
Negative pi over 2.
Yes. Why is that the case? That's because the sine of negative pi over 3 is the same thing as the negative of the sine of pi over 3. But that's just the same thing as negative. So when we take the sine inverse of both sides, the sine inverse of this is just not negative pi over 3. So we get negative pi over 2, negative pi over 3, negative pi over 6. What comes after that? Oh, this should be pi over 4. Negative pi over 6. 0 is 0. Right? For instance, why is sine inverse of negative 1/2? It's equal to some theta, right? We can take the sine of both sides. And when we get the sine of theta is equal to negative 1/2. So it's asking you a question. At what angle is the sine equal to negative 1/2? That's negative pi over 6. Because in a unit circle, at positive pi over 6, cosine is root 3 over 2, sine is 1/2. But at negative pi over 6, cosine is root 3 over 2, but then their sine becomes a negative 1/2. That's why it's saying negative 1/2. So that means now when I plug in a negative 1/2, I should be getting a negative pi over 6. So I'll put them here. So at negative 1/2, it outputs a negative pi over 6. At negative root 2 over 2, it outputs a negative pi over 4. At negative pi over 3, it outputs a negative root 3 over 2. At negative pi over 2, it outputs a negative 1. So notice, so far, it looks like the sine curve, but just truncated. It doesn't look very curvy because I don't plot things very well, but the curve, if you plot it really well and you draw everything to scale, it looks like this. Really, that's just the piece of the sine curve. Just flipped. It's just rotated. So if we have your theta, your sine of theta, it's this part. Does that make sense? We get the whole thing all the way, we rotate it, and we chop off the white curve, and you get this yellow curve. Why are we even doing that? Well, we must restrict the range, because if we let this go a little further, then this does this. Why is that a problem?
Because then I can't pass the vertical line test.
Aha, correct, Pam. Because then it won't pass the vertical line test. It ceases to be a function if you allow it to go any further.
Technically speaking, this isn't necessarily like a straight line, is it?
No, it just looked like a straight line on this graph. Visually, it looks more like this yellow, the curvy line. The way I've drawn it kind of looks like a straight line, and for that reason, I reproduced it again.
Well, just a minute kind of looks like a tangent.
Yeah, well, you know what? Why don't I use technology that can graph better than me? You guys see that? So that is what's going on here. What I'm telling you is you get this part of the sine wave that right here is at negative pi over 2, and right here at positive pi over 2. From this domain, notice that the domain becomes the range now, and you rotate it. Over here, you have lengths. This is positive 1 all the way to negative 1. So the range, for sine of theta, okay, it had a domain negative infinity to infinity. It had a range negative 1 to 1 inclusive. But when you flip it and you get sine inverse of a L, its domain is now the possible angles you can input, or the lengths that you can input. So the lengths vary from negative 1 to 1, and the output is angles, but the angles can only range from negative pi over 2 to pi over 2. Notice that this range goes to that domain, and this domain goes to that range. But why is that not negative infinity to negative infinity to positive infinity? So that's because we have to truncate it. If we allowed it to be negative infinity, it would just be like this, and it would miserably fail the vertical line test over and over and over an infinite amount of times. So we must truncate it. We must restrict the range to negative pi over 2 and pi over 2 so that it continues to be a function. So now you're introduced to sine inverse. It is indeed a function, and its domain is negative 1 to 1, and its range is negative pi over 2 to pi over 2. Okay, so that's what that graph looks like. Let us keep that up so that I can use it to graph while I do the math up here. What is the cosine of pi over 6? This should be instant, guys. At this point of the semester, you should just know that right away. Yeah, pi over 6 is root 2. All right. So what was the cosine of 0? Cosine of 0 is 1. What's the cosine of pi over 4? And what's the cosine of pi over 3? What's the cosine of pi over 2? So what we ended up creating is a This is a theta, cosine of theta table. But notice that cosine of theta equals a length. So inversely, we can create a length which is cosine inverse of theta table. Where, guess what? When you take the cosine inverse of both sides here, you just get a cosine inverse of 1 outputs what you think, a 0. You get a cosine inverse of a root 3 over 2. It outputs what you would think, pi over 6. Cosine inverse of root 2 over 2. Outputs what you think, pi over 4. I decided to draw the tables right next to each other so you could see it, how obvious it is. You could do this for sine as well. Cosine inverse of 1/2 pi over 2.
Professor, shouldn't be the
Oh, 3.
cosine inverse, shouldn't that be under the cosine inverse of theta?
Yes, yes. Yeah, the angle should be on the left, you're right, and the length should be on the right.
Okay,
You're absolutely correct. Mhm. Because you flip them. So they had not been flipped. They had been flipped in my mind, but not on the board. That doesn't count though, right? On your exams, you can't be like, well, I got the right answer in my mind. That doesn't count. So then cosine inverse of 0 gives us our pi over 2. So you could continue to do this. All right. You can even say, what's the cosine inverse of -1/2? What do you think you're going to get?
-5/6.
Well, we don't have to be. If we don't know what this is, here's what you can say. It's a theta, isn't it? It's an angle. We can set up this equation. Then we can take the cosine of both sides. So we get cosine of theta equal to the cosine of cosine inverse, -1/2. So we get cosine of theta is equal to just -1/2. So this means, what is theta? Theta is the angle at which cosine evaluates to -1/2. And there's many of them, right? Because there's many of them, so cosine inverse of -1/2 is equal to the which thetas? Well, I know one of them on our unit circle. Let's go to our unit circle here. Well, right here at this angle, 2 pi over 3, cosine of 2 pi over 3 is -1/2, is it not? But also over here at this angle, what angle is that? Well, if this angle is 3 pi over 2, 30, 60, 60, or 30, 15, 15, 30 tells me that I can subtract the 15-degree analog to figure out what that angle is. Multiply top and bottom by 3. I get 9 pi minus a pi all over 6. That's 8 pi all over 6. That's 4 pi all over 3. So the other one is 4 pi all over 3. So which one do we pick? If we want cosine to be if we want cosine inverse to be an inverse function, it can only have one of them.
2 pi over 3.
You said what?
Let me pick 2 pi over 3 because it's the next.
Yeah, you can pick 2 pi over 3. But if we want to continue to make it a function, we have to restrict the range now. So what is the range that we want to restrict it to?
0. No. From pi over 2, negative pi over 2 and pi over 2, right?
Negative pi over 2 and pi over 2. So over here, we were good until right here, weren't we? Okay. So you're saying, okay, just go from negative pi over 2 to pi over 2. Meaning, if we continue the table on, what about cosine inverse? What length should we put in?
I'm not understanding.
Oh, what am I doing? Just cosine. Oh, come on. What's going on there? What's going on here? So what used to be the x-axis, which was the theta axis for sine, is now the range axis, right? What was the range of the cosine function? I think the table stuff is enough for now. What was the range of cosine of theta? The range equals what? Negative 1 to 1. The domain equals what? Excellent. So now cosine inverse of a length. Notice that this equals a length. What is the range of this guy? And what is the domain of this guy? We know the domain is what the old range was. Negative 1 to 1. So we're on a good trajectory here. We're going from 0 to 1, and we probably should now input negative 1/2. Negative root 2 over 2, negative root 3 over 2, and then negative 1. Right? What is the range going to be? It's not negative infinity to positive infinity, is it? What are we going to restrict the range to be?
Pi over 2 to pi over 2.
Yeah, we tried that and it was reproducing multiple inputs right here.
Okay.
So what we want to do is just try 0 to pi. So let's see here. Here's our cosine inverse. We'll let this stay. And we're just going to continue the table. Continuing the table on here. Here's theta. Here's cosine inverse of your length. 1, root 3 root 2, root 2 root 2. 1/2, 0. Now what?
Negative 1/2 would be negative, or cosine inverse of negative pi over 3.
Yeah, the cosine inverse of negative 1/2 would be what?
Negative pi over 3. Well, that's from 0.
So notice that that's not in our range.
Yeah. That's from 0 to pi.
So cosine inverse of negative 1/2 is equal to some theta. Take the cosine of both sides, you get negative 1/2 is equal to the cosine of theta. Remember, I just drew it and I erased it. But at this angle, 2 pi over 3, that's the angle we want because that's within our range. The other angle was over here. And it was 4 pi over 3, and we don't want that one because that's beyond the pi. We want it to remain in our range.
And it would be 2 pi over 3.
Yeah, we'll choose 2 pi over 3. So what about cosine inverse of negative root 2 over 2? All you need to do is to get that 2 pi over 3. It goes 30, 15, 15, 30. So that was 30. We got to add a 15-degree analog. Multiply top and bottom by 4. So that's pi, 3 pi over 4. So this becomes 3 pi over 4. The next angle will be 3 pi over 4 plus another 15-degree analog. So what's the cosine inverse of negative 1? It's asking you at what angle does the cosine evaluate to a length of negative 1? At what angle does it do that? That angle is pi. And that's the same thing you get as when you do 30, 15, 15, 30. So we add a 30-degree analog to 5 pi over 6. That's the reason. So when you plot it, it looks like that green function over there, where your inputs were lengths and your outputs are now angles. And this in the yellow is cosine inverse of L. Over here, its domain is from negative 1 to 1, and its range is from 0 to pi. Now, let's move on to tangent. Is tangent just going to be sine over cosine? Actually, how do you take the ratio of those two weird squiggly lines? Truth is, you don't. You think about it algebraically, just like we are right now. And it will do something like that. Let's do the same thing we did before. Let's start with a tangent of theta, theta table. What is tangent of 0? That's sine of 0 or cosine of 0. That's 0 divided by 1, which is equal to 0. What about for all the other ones? Pi over 6, pi over 4, pi over 3, pi over 2. What is the tangent? Pi over 6. That's a sine. Pi over 6 divided by cosine. Pi over 6. What does this end up becoming? When you rationalize, right? What is the tangent of pi over 4? One. Why is that the case? Anything divided by itself is 1. That's why. What's the tangent of pi over 3? That's the sine of pi over 3. Or the cosine of pi over 3. That's root 3 over 2 divided by 1/2. That's equal to cancel out the 2's, we just get a root 3. And what is the tangent of pi over 2? This one's really easy. Come on. Nothing goes wrong here at all. Nothing goes wrong here at tangent of pi over 2.
It's 0.
No, it's not 0. Something goes terribly wrong. Well, sine of pi over 2 is 1. Cosine of pi over 2 is 0. So we're dividing by 0, so this is undefined. Or you could say positive infinity. Okay. So what are these values for different inputs? Let's continue the table. Well, it messes up there. So why don't we go from like 0 to negative pi over 2? So negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2. What is the tangents in these cases? Well, it's actually because tangent is an odd function. They're all just the negatives. Notice that the tangent, for instance, of negative pi over 4 is equal to the sine of negative pi over 4, or the cosine of negative pi over 4. Sine is an odd function. Cosine is an even function. But you still preserve the fact that it's dividing by itself. That becomes a negative 1. This is a negative 1. Just like negative pi over 6 will be a negative root 3 over 3. Just like negative pi over 3 will be a negative square root of 3. And just like negative pi over 2 is going to have something go wrong with it. Let me show you what's going to happen at negative pi over 2. Sine is an odd function. Cosine is even. But you know what? Potato, potato, it doesn't matter. Sine is pi over 2 is 1. Cosine of pi over 2 is 0. So now we get something analogous to like negative infinity. So let's plot it. Okay, and that's not even what we want to plot. We tabulated tangent because it was intuitive and easy. What we really want to know is what is tangent inverse. So this is equal to an L. So now theta comes on from being in the domain, now it's in the range. Now the L is equal to the tangent inverse of theta. Maybe I created enough intervals there. So let's start with all the way negative pi over 2. The angle is, or the input is a length. So this will confuse you. What am I doing here? No, actually, I have this in the right spot. I need to put my negative pi over 2 over here. Pi over 6, pi over 4. What am I doing? This is pi over 3. This is 4. This is 0. There we go. So now the outputs are angles, the inputs are lengths, and we're going to input it into a tangent inverse. And we give it a length, and it's going to output an angle. What were the lengths that we gave it? Well, this was negative infinity, negative root 3, negative 1, negative root 3 over 2. Okay, and then for 0, it became 0. And then, oh, it flips, it just becomes the positives. So what does this graph look like? Well, tangent inverse ends up looking like this. Or, well, that's what I'm trying to say is you get that function and you rotate it. So your tangent inverse actually looks like this. With asymptotes. Where are the asymptotes at? It's when division by 0 is occurring. Division by 0 occurred where? Pi over 2, negative pi over 2. And notice at negative pi over 2, the function is headed towards negative infinity. What's yellow is the tangent inverse of a length. So all of the asymptotes will be located at get this value and add a pi to it. Get this value, add a pi to it. So over here is 3 pi over 2. Over here it's negative 3 pi over 2. See, that graph I did is not bad. Actually, out of all the graphs we've done. Okay. And I messed up by calling this tangent inverse. This is your tangent of theta. What I was drawing before, and that I erased, so maybe I have space over here, was what happens when you take the inverse is you get this guy and you rotate it. And this is what you get. Where the vertical asymptotes have now become horizontal asymptotes. And this is your tangent inverse of a length, outputting angles. So up here, we get positive pi over 2, negative pi over 2 over here.
And it just outputs one of them right now, like multiple, the way it does with the tangent.
Right, because notice that this passes the vertical line test. Notice that it passes the vertical line test. If we then were to not restrict the range, then we get this thing happening. And notice then it won't pass the vertical line test. Okay, that's all for today. I'll upload your homework soon. You too.